Polarization due to impurity atoms in a solid. The following represents a simple two-dimensional model of a situation of actual physical interest. A solid at absolute temperature T contains n sub 0 negatively charged impurity ions per unit volume. These ions replacing some of the ordinary atoms of the solid. The solid as a whole is of course electrically neutral. This is so because each negative ion with charge minus E has in its vicinity one positive ion with charge plus E. The positive ion is small and is thus free to move between lattice sites. In the absence of an external electric field, it will therefore be found with equal probability in one of the four equidistant sites surrounding the stationary negative ion. If a small electric field epsilon is applied along the x direction, calculate the electric polarization, i.e. the mean electric dipole moment per unit volume along the x direction. Okay, so in the problem we're applying an electric field in the positive x direction. So this is the direction of the electric field. As you can see, x is shown here as pointing to the right. And let's remember what we mean by electric dipole moment. The electric dipole moment for two charges Q and minus Q separated by a distance d is defined as this is a vector. It points from the charge minus Q to the charge plus Q, the polarization vector P, and the distance between these two charges is D. So magnitude wise, it is P is equal to Q times D, and direction wise it's pointing from negative to positive charge. Okay, so in the case of the problem, we are describing the placement of the positive ions in four equidistant sites with respect to the ion. So we can have four possible scenarios. So let's talk about those scenarios. So here I have my negative charge minus, and I can put my positive charge here at this site, so to the left of this charge, or I could put it on this site here. It would be possible to put it here as well. And looking at the lattice here, the distance between two positive charge possible locations is A. That is the lattice constant A. So the distance here between this site and this site is A. So since this is part of a cube here, you can see that uh, by completing the right triangle here, I can see that the distance between the negative ion and positive ion will be, because this is A over 2 and A over 2 here, so it will be equal to uh, A square root 2, because this part is also A over 2. So this will be equal to A square root 2 over 2. So you would have A square over 4 plus A square over 4, uh, which is A squared over 2, equaling A square 2 over 4, which is A square over 2. So the distance between the two charges in this case is A squared over 2. Now what we're interested in is the mean electric dipole moment per unit volume along the x direction. So what is the x component of the polarization vector? So the polarization vector points from the negative charge to the positive charge. So this is my p vector. However, its x component is here. This is px. So the x component is minus q a over 2 I hat. So it's in minus I hat direction. So it is minus q a over 2 I hat. On the other hand, if I had it in the other side, so if I had my positive charge, so let's put my negative charge here again. Now if I put my positive charge here, and the other possibility would be to put it here, then I would have the polarization vector pointing from minus to plus in this direction, and then the x component would be pointing in plus I hat direction, and in this scenario I would find that the x component is plus q a over 2 I hat. So as you can see, I have 4 possible sites. So if the charge is to the left of the positive charge is to the left of the negatively charged ion, for either it's at the top or at the bottom, I have the same x component, minus qa over 2 I hat. And for the scenario where it is to the right of the negatively charged ion, it's always plus qa over 2 I hat. That's the x component. Now, having talked about the polarization vector, we can remember what is the energy of the dipole moment, the electric dipole moment, inside an electric field. This is the dot product minus p dot epsilon. So if the electric field is pointing to the right, the polarization vector also wants to point to the right so that the energy will be minimized. So this is the energy of a dipole inside an electric field. So preferentially, this is telling us that preferentially P points in the direction of the electric field. And you can understand why this is so, because if you go back here, so if you have the electric dipole moment vector pointing from minus q to plus q, so if you put a minus charge here and a plus charge here, and your electric dipole moment points from minus to plus, And if you place this inside an electric field epsilon, what you would see is that the reason you have this electric field epsilon is there is electric field always points from a positive charge distribution to a negative charge distribution, and you can see that the positive charge distribution will be attracting the minus side, negative charge distribution will be attracting the plus side, so you can understand why the polarization vector should be pointing or wants to point to minimize its energy in the direction of the electric field. So the energy of a dipole is minus p dot epsilon. So I have two possible scenarios. The positively charged ion to the left of negatively charged ion, then in this case the energy of this configuration would be equal to minus, since the x component is minus qa over 2 I hat dotted with electric field in positive x direction I hat. So the energy of this configuration would be qa over 2 epsilon. If the positive ion is to the right of the negative ion, E right, in this scenario I would have minus plus qa over 2 I hat, the polarization vector, dot product with epsilon I hat, so minus qa over 2 epsilon would be the energy. And these two are actually degenerate energy levels, because I have two possible configurations that correspond to these energies. Two sites to the left and to the right will satisfy this energy. Okay, so I have basically, you can think of this as having two energy levels. The right energy level or the left energy level is the higher one. The left energy level is plus qa over 2 epsilon, and the right energy level is minus qa over 2 epsilon, and it has a degeneracy of 2 for both of them because there are two possible configurations. So the probability of occupancy of this energy level, p left, let's say, is a constant c times e to the minus beta qa over 2 epsilon. And p right is c e to the beta qa over 2 epsilon. So this is when the position of the ion is at x equals minus a over 2 component, and x component of the position vector is plus a over 2. So it is to the right of the negatively charged ion. Now these two probabilities, so it's either to the left or to the right. And normally I also have to put 2 here, so you can see that there should be a 2 here because I have a degeneracy of 2, but I can absorb that into the constant c and make it c prime, let's say, because I have degeneracy. Okay, so p left plus p right, the probabilities should add up to 1. So let's call this or keep it as a c prime. So I can say that this is a c prime. or let's define 2c as c prime, then I would have c prime times e to the minus beta q e to the minus beta qa over 2 epsilon plus e to the plus beta qa over 2 epsilon, and this must be equal to 1. So I find that my constant c prime, the normalization constant, is 1 over e to the minus beta qa over 2 epsilon plus e to the plus beta qa over 2 epsilon. So basically I have the probability distribution found here. So the question was the mean electric dipole moment per unit volume along the x direction. So I can calculate the mean position of the positively charged ion. Okay, so let's calculate the mean position x component of the positive ion, positively charged ion. So that would be equal to x bar. Now, so the probability p left for x is equal to minus a over 2. So I have the following situation here. So x can be, the x component can be minus a over 2, which means it's to the left. And the proportionality, well, the probability is e to the minus beta qa over 2 epsilon for this scenario. Or the x component of the position vector could be plus a over 2 with e to the beta qa over 2 epsilon, and then here I have the partition function e to the beta qa over 2 epsilon plus e to the minus beta qa over 2 epsilon. So this would give me the mean value. Now I can rewrite this as, if I take this into a over 2 parentheses, I can rewrite it as e to the beta qa over 2 epsilon minus e to the minus beta qa over 2 epsilon divided by e to the beta qa over 2 epsilon plus e to the minus beta qa over 2 epsilon. So we can check if I did this correctly. So I had plus a over 2 e to the beta qa over 2 epsilon, and indeed I have that, and that I have minus a over 2 e to the minus beta qa over 2 epsilon. If you distribute a over 2, you will see that this is correct. Now what I have here is e to the x minus e to the minus x divided by e to the x plus e to the minus x. This is tangent hyperbolic x. So I can see that my x bar is equal to a over 2 tangent hyperbolic the charge q that I have called q here is electron charge E. So EA, so q is E, the electron charge, qa epsilon divided by 2 kt. So I also substitute for beta 1 over kt. Okay, so that is x bar. Now if you look at the mean value of the polarization, um, as you can see, for the x component of the polarization, I have to multiply q with the mean x position, x component of the position vector of A. So the total polarization is sum of all the polarizations mean value divided by the total volume. So if you have the total number capital N divided by the volume multiplied by p bar, you will have basically the number per volume was given as N0 here. It contains N0 negatively charged impurity ions per volume. So that was N0. So N is number of negative ions, total number. N0 is N divided by B, volume. So we have N0 times the electron charge E times X bar will be my answer. So since I know already what X bar is, the total polarization, the electric dipole moment per unit volume will be N0 E X bar, which is N0 E A over 2 tangent hyperbolic EA epsilon divided by 2 KT. So this will be the final answer for electric dipole moment per unit volume mean value, which is the polarization, what we call polarization. Okay, so we're talking about a model of a crystal lattice of a solid where we have a mobile positive charge that can be in any one of four equidistant sites from a negative charge, and in the absence of an electric field it can be in any one of these sites with equal probability. But when we turn on an electric field, because the electric dipole moment will interact with the electric field and the interaction energy is minus p dot epsilon, it will have a preference. So the question is, in the presence of an electric field in the positive x direction, what is the mean electric dipole moment per unit volume? That is, what is the mean value of the electric polarization? So this is mean value of electric polarization. Okay, so first of all, we have to remember polarization, the electric dipole moment vector points from minus charge to plus charge. Its magnitude is q times d. So here q is the electron charge E. And if the ion is placed to the left of the negatively charged ion, the positively charged ion is to the left, then you can see that the x component of the electric dipole moment will be minus qa over 2 I hat. If it's to the right, it will be plus qa over 2 I hat. And writing the energy for these two configurations, if it's to the left, energy is qa over 2 epsilon. To the right, it's minus qa over 2 epsilon. And that corresponds to two possible configurations for the positively charged ion. So we have a degeneracy of 2 for both energy levels. So it doesn't matter if we take this into account or not. So the probability of occupancy of the left side is 2c e to the minus beta qa over 2 epsilon. That corresponds to a position vector x component of minus a over 2. And if it's to the right, it's e to the beta qa over 2 epsilon with 2c, when x is plus a over 2. And it should be normalized, so we find that c is 1 over the partition function, which is normally twice of these two factors, but because the 2's will cancel here, so it's actually what we have in the denominator is partition function divided by 2, but that doesn't matter because the 2's will cancel. Okay, so I can see that the mean position of the x component of the positive ion is then tangent hyperbolic a over 2 tangent hyperbolic ea epsilon over 2 kt by substituting for charge E and beta 1 over kt. Well, but the polarization is number of ions per unit volume times the charge times the distance. So we have n0 times E, where n0 was the concentration of negatively charged ions, multiplied by the charge E and multiplied by the mean position x component, x bar. So the final answer is n0 ea over 2 tangent hyperbolic ea epsilon over 2 kt.